Hello, I'm Dr. Wendy Bazilian, and I'm delighted to be here today with Dr. Richard Bazinet. Dr. Bazinet is a professor at the University of Toronto. He's a professor in the Department of Nutritional Sciences and the Canada Research Chair in Brain Lipid Metabolism. He is a leading researcher in omega 3s and the brain. He and his team are known for pioneering studies using tracer and isotope techniques that we'll talk a little bit about today to track how the omega 3s, and in particular some plant based omega 3s like ALA, that come from things like chia and flax and ahiflower and walnuts, how those fatty acids contribute to DHA in the brain and in the body. And he's just been recognized with the prestigious Sapelco AOCS. AOCS is the American Oil Chemists Society, the AOCS Research Award, honoring his outstanding contributions to lipid science. So today we want to talk about his work, what it means for understanding omega 3s, and why this science matters for all of us. This is one of the most respected honors in lipid science, Dr. Bazinet. So it's a big deal. And I think it's such a good launch point, to sort of tell us. So, congratulations on this award, and to briefly tell us what this recognition means for you and your lab's work and what it means for the field of science and lipids.
Well, thanks, Wendy. That's very kind of you to say that. Yeah, it's quite an honor. We're very excited about it. The award is for our research, and research is a funny business. Sometimes you do things, you just do them because they're interesting and you like them. But there is something nice when your work gets cited or used, and you get these recognitions. It's kind of a hint that you're going down maybe the right path or answering some questions that other people are interested in.
Yeah, I think that validation point, it is such a good recognition. So, I mean, congratulations. It isn't so nice to have little milestones along the way, suggesting you're on the path, or on a path or an exciting path. I think it's also so meaningful for people outside of the science community too, to see this validation for your contribution. So I think it's impactful for, us recognizing it, not just that your lab is honored in your research, but as a jumping off point to talk about, what's really important here. What is this sort of new science that is being acknowledged that you and your team are leading? And I want to start on, I don't know if I should call it myth busting, but on a misunderstood part of the science that you are, unwinding and setting new course for. And that's sort of the conversion story, as if for lack of a better word. For years, we've sort of heard that ALA doesn't convert well. Those of us who've like sort of dabbled in the science or even deeper, just inspired by it, that ALA, the alpha linolenic acid from plant-based sources, is not efficiently converted to, upstream to DHA ultimately. But it might be misunderstood or missing or an old view. So I am such an advocate of science and the evolution of science. So it's not something like it's bad science. Now we've got the right science, but what has happened? You've introduced new terms, and are we talking about the wrong thing, or what should we talk about now? So can you tell me a little bit about this sort of misunderstood thing called conversion?
Yeah, so I think there's a couple things that have collided in this world. And we're going to focus in on the brain. So if somebody's interested in the toenail or the heart, I'm not going to go there. They might be a little different. But there's a lot of this omega 3 fat in the brain called DHA, docosahexaenoic acid. It's kind of famous nutritionally because it comes from fish or from conversion from ALA, right? And so forever, we thought the conversion rate was low. I didn't like that answer because part of me is like, well, it's low, but how much do you need, right? To say something's low is a relative term sometimes, especially if you don't know how much you need. I make analogies with this with money. If I gave you $5 today for your work, you'd probably say that's low. But if you didn't have any expenses and you only had to buy a piece of gum, it's enough, right? So we need to figure that out. And so I was involved in some studies, and there were some ongoing studies when I was a postdoc back about 20 years ago, looking at how much DHA gets into the human brain. And they found that about 3 or 4 milligrams of DHA gets into the human brain every day. And I remember sitting around the labs at the time, and when that number came out, my guess was it was going to be 50. It was just my guess, right? And number comes out, and you're off by more than an order of magnitude, tenfold. What can you
Yes.
say? So that number was low, a lot lower than we expected. And then one of the things we were able to do, there was some controversy because there's, DHA in the brain. It's like there's something in a house and there's a whole bunch of doors and it can go in a variety of doors. And if my colleagues had the wrong door, they would have underestimated it. So one of the things our research did was able to confirm that that in fact was a good estimate. And I think that was important. And then that set me off the path of saying, okay, well, if the brain doesn't need much, and we can't convert very much. Can we convert enough? And we started to challenge those numbers from the brain's perspective and say that, hey, this low conversion rate actually has a lot of implications for low conversion. We've put papers out arguing that we think you can convert enough for the normal brain, right? The developing brain's a little different, and maybe diseases could also be a little bit different also. So I'd say it was how DHA gets into the brain, and using quantitative approaches on that was able to collide with some of our new work and reassessment of a low conversion rate.
Interesting. So, in simple terms, and you sort of did it with the dollars and cents of it, if it's enough, if we don't need much, but we convert enough, then maybe it's the wrong question in the first place, whether that even matters. And now we're able to see roughly how much for a healthy brain we need. And as a result, you've started introducing, or, I mean, the natural segue seems to be that you've been observing things like turnover, or I've heard you say in other conversations, like popping off, or thinking about the body's economy and, sort of the common sense of this, really, to an extent that you're showing through science of the efficiency of the body to, if it's enough and they take it in, then it's enough, period. So I'm just curious about how turnover and half life and these terms that are used, they may sound really technical, but in plain terms, how much the body actually needs is what you're getting at. And then you're starting to map where it's traveling to or how it's getting there in the first place. Is that right?
Yes, exactly. So this low uptake rate into the brain of 3 or 4 milligrams can also be exchanged with what we call half life. And that's how long does it take for the DHA to leave your brain, for half of it to leave your brain if none was being replaced, more or less. And that number was also surprising to me because it was about 2 years. And this, it's surprising, but it makes sense, right? We learn in physiology that the brain gets priority, the brain gets everything. If the brain had this really high requirement for these omega 3s, we'd have problems. We'd have problems all over the place, right? Because these omega 3s are extremely important in the brain. They're highly abundant in the brain. And we're using them right now in our conversation, right? They're being consumed. But the rate of their consumption is fairly low, and we're able to replace that. So I guess it makes sense, in hindsight, that we wouldn't have a massively high nutritional requirement for these for the adult brain. And what we're able to work on now is a couple little things that are a little tricky in our field. Is sometimes you consume a molecule and the blood levels go up or the tissue levels go up, and that's fine. And people often think like that. But sometimes you consume a molecule and you just replace what was left, what was consumed metabolically, right? So I like to think about this as taking a snapshot of a parking lot or a freeway with a camera on a drone, right? And you see the parking lot, you're like, wow, there's a lot of cars here. This is the one, right? This is where all the action's happening. But the freeway, they're moving quite quickly. And you lose that when you just take a snapshot picture. And what we're doing with these turnover or kinetic approaches are looking at the speed of things. And we're seeing that the speed by which precursors to DHA, we haven't done them all yet, can turn it over seems pretty adequate to maintain its levels in the blood. And, we think that's supplying the brain to keep everything kind of in balance.
Fascinating. I mean, sometimes it's like we're not able to catch the whole story because it's a dynamic story. You're catching a time point, like you said, the parking lot at a given moment, or the drone, the bottleneck traffic that we've all sat in before. So I guess the idea that conversion being high or low becomes less and less relevant if it's sufficient for the brain. If you're looking at the turnover and starting to get a little bit of information about the kinetic nature, if I'm saying it
Yeah.
right, of
Yeah.
the omega 3s coming in through the body. So that sort of brings me to your new science, and it's not new for you because you've been, doing this now for enough years to be really recognized by your peers and publications and awards now. But tell me a little bit about the tracer isotope studies in simple terms, if you
Yeah.
can, though it's very technical and very complex. How is that changing the understanding of how ALA contributes to DHA in the brain? And in a small way, what is it? What are you
Yeah.
doing in the lab?
So one of the things that's difficult with molecules is they kind of all look the same under most instruments, right? And you can't tell if I measure a DHA in your blood if it came from a fish you ate last week, if the fish you ate today, or something you synthesized this morning, right? The molecules always look the same. These molecules are made out of carbon, and sometimes some of the carbons can be a little heavier. And we've been able to get instruments, very, very big instruments that make a lot of noise, are very expensive and are very fussy. But when they work, they can see the little differences in the carbons and the ones that weigh more and the ones that weigh less. And so, what we're able to do is we're able to feed people either the DHA that weighs a little bit more or the precursors that weigh a little bit more, or we can make them a little lighter. And then we can look in the molecules and say, hey, where did you come from? What was your source? And so we're using this new technology to assess the turnover of DHA and some of these other molecules. We've done a lot of the work preclinically, but we've recently got into analyzing some old clinical trials that were done. And we completed our first clinical trial just a few months ago, and we're starting to present some of those results out there.
Exciting. Wow. So, I mean, what keeps popping to my mind is sort of like GPS tracking or like air tags or something like that you're able not to just measure a time point, but like follow the journey, and track where they are in their path, it sounds like, so that you can not just measure an end result, but actually follow along.
Yeah,
It
it's
sounds
it's
like,
like
I
going
don't
back
know.
to that parking lot and freeway. We're able to color the cars or certain cars, right?
Okay.
And then we can see if they're red cars, we can see how many are going by and how many are coming into the parking lot. And then by using that, we can get the speed of these reactions and a better idea of these rates by having that kind of tracing technology with molecules that we can do to a certain extent in humans, right? It's always going to be hard to do it in the human brain, but we're clipping away at that.
That's exciting. So I'm thinking you're quite a detective, Dr. Bazinet. This is your detective story as it starts to unfold the tools, magnifying glass, looking at the dynamic journey here. So I would like to think about, well, continue, please.
Yeah, yeah. So you say detective. We're stealing this technique from detectives to some extent.
Oh,
So sports doping, what they do, one of the things is that your testosterone comes from, you make it in your body from a precursor, and if you made it from that precursor, it should have the same weight kind of as the precursor. If it doesn't, you cheated. You got an exogenous source of testosterone that was made somewhere else, and the weight is kind of mismatched. So we're doing stuff like that, just not with testosterone, with other molecules, and saying, hey, where did you come from, right? Did you come from this source or that source?
yeah. Oh, well, that's a great bridge between different uses of technology and different tools of science
Mm.
and their variable applications. And the benefit of still being human in this world, right? To be able to use our brains to come up with like, oh, I see they're doing it that way. I wonder if we could apply that to something else. I think that's in my book uniquely human. So there's hope for us yet. And speaking of humans, I want to just talk about like why this matters for people. What does this research mean for someone who's consuming omega 3s, like the ALAs from things like chia or ahiflower, flax, which I know is big in Canada, walnuts, plant based sources. Should we be thinking of ALA fatty acids? I know they're essential, like in nutrition field, they're the essential fatty acid, but they often come off to media and other environments as sort of secondary because of this previous conversation we've been having. What does this mean to us? Do they become more central to the omega-3 story?
Yeah, so I think there's a few big moving parts coming through. One is there's countries saying, hey, we need to eat more plant-based diets, okay? And food policies saying that. You've got environmental issues with ecology and a variety of food sources that are sensitive to it. People are working at that as well. And you've got people concerned about ethics and the ethics of the food choices they make, right? And when you put all of these things together, and I don't want to poo poo on any of the other sources, and people are working on them, they're doing a very good job at that. Plants are relatively simple, a relatively simple solution, right? The ethics are pretty good. Sure, there's ecological issues, but they seem less than some of our more carnivore based foods in that respect. So then the question becomes okay, so if we're going to switch to these plant sources of ALA, and everybody's been saying you're not a good converter, you're not a good converter, then I think this is the context that we're testing these in, and we're saying, hey, wait a second, the brain needs a little less than we thought it did, the adult brain. And this conversion rate thing's a little misleading because the speed is actually a little quicker than we think it is. And it looks like in some cases we can feed things and the DHA can disappear from your blood and be replaced by synthesized through synthesis just as fast as it's disappearing. There's still a little bit more work to do in there. That's like, hey, wait a second, this is another solution to that puzzle, and maybe an easier solution. Time will tell on that, but it's got a lot of implications.
Yeah, that's so interesting. I think that maybe it makes a nod to variety in the diet too. I mean, you've proposed, the ethical, environmental, the personal, the plant-based movements, which is, also policy and politics sometimes. There's also the practical aspect, for a long time, some of the plant-based sources may have been framed as sort of more nice to have, or alternately, some of the other sources are less obtainable no matter what because of economics or availability. If you're totally landlocked, maybe marine sources aren't handy for you because these are fats we do have to seek in the diet and through real food sources. Certainly not just supplements, although those are out there in the marketplace too. Seems like some of the commodity groups and some of those who are interested in investing in research also in this area are sort of like becoming scientific catalysts, as is your laboratory, sort of pushing just for the discovery of mechanisms and opportunity in the pursuit of public health, maybe for humans. Optimistic about it all.
Yeah, yeah. So I think, as one of the things our lab, we're methodologists to some extent. So sometimes I joke and say we make a method and then we hope somebody has a question with our methods. And some of our methods have worked better than others. But this method that we're using now with these isotopes, it's almost a little misleading because what we've been able to do with this fancy instrument is not go buy isotopes from from these companies, sorry, they're very expensive and very hard and very tricky to use. But we can use different food sources, and because of the precision of our instruments now, I can look at a molecule like DHA, whether it came from fish, whether it came from algae, or whether it came from somewhere else, and it behaves like an isotope. And by bringing this kind of methodology forward, we're really able to drive the price down. Now, the instrument costs are quite expensive, but after you get the instruments set up, the methodology becomes quite cheap. And I've made some jokes in some presentations with some preclinical studies that it would have cost us $1 billion or $500 million to feed the rodents for the study, whereas it really only cost us like $1,000. So and I probably have an error in my estimate of $1 billion. I didn't ask for a discount, a
Yeah.
bulk discount, but the prices have really come down. So it allows, I think, more of these commodity groups who are interested in research but can't be doing $1 million studies all the time to do some preclinical work to find out what looks most promising, and then go forward and prioritize some clinical studies. Right, really try and push the translational work.
Yeah, yeah, your research there and the replication of it and the methods, in science, methods are so key. It's all about the planning, right? For the outcomes to be believable, credible, whatever the result is. So it really suggests that your research, if you get into the weeds, if you come into your lab, which I'd like to do someday, and I saw at face value, it's probably be intimidating. But at the end of the day, what you're doing is you're giving sort of like hope for real food. I mean, that we don't just have to pursue supplements to survive on this planet or a certain kind or source, maybe, but that they have a wide variety of validity for this course of action. Talking about the brain, you said we're talking about the brain, not the toenails today, but the
Yeah.
brain. But that there's ideas that the variety in the diet, plant-based sources may be an option. I imagine that one of the challenges for you also is that just fats in the brain are so misunderstood and so complex. I mean, it must be challenging. You do such a good job about it, but they're either like oversimplified or overcomplicated, and it leaves us all, you know, brain tied, like tongue tied, but the brain.
Yeah, yeah. People don't realize, right? Your brain's almost as fat as your body fat, but it's a little different, right? Whereas your body fat's kind of this saturated, monounsaturated mixture. Your brain's got a fair amount, but not exclusively these very long chain polyunsaturates. It's a bit different that way. And then, luckily your brain's in a skull, so that means it can't keep growing endlessly like our body fat could if it, if given the opportunity. And that restriction on brain size has a lot of implications for these low numbers I think we were speaking about, right? And why we have a turnover rate that's a fairly long period of time going on. So it's kind of, yeah, misunderstood a little bit. It's fat, but it's a different type of fat and it's regulated a very different way. It's really a phenomenal tissue. It's really exciting.
Would you have ever thought you were gonna be in this space today? I mean, I was gonna just about to ask you about looking forward, but I would have to say looking back, I mean, if 10 years ago, well, maybe you're starting that, but 20 years ago, would you say, "This is the frontier I see myself in"?
So there were a few fun things that happened, right? So I did my PhD on these omega-3 fats and inflammation in the periphery, kind of like body inflammation. This was getting back into the late 90s, and that field was starting to get exciting because people had identified that there's anti-inflammatory effects of some of these omega-3s. And then I went and did a postdoc in the brain on a more or less on a different lipid, but we realizing that the brain had a lot of this DHA in it. It all started to collide. I met somebody from France who was very interested in the role of this DHA in inflammation, and it was like it made sense if you have a brain that's somewhat of an isolated immune system to put a lot of these important molecules in. And we worked on that. We call it signaling sometime. And then part of me was just because of the training I had was really interested in putting numbers to things, right? Like low, how low? Give me a number, right? High, how high? How much? Eat more, how much more? Like get away from these vague terms. And by putting the numbers onto things, I think we've been able to map out a little bit of the puzzle a little bit better and identify a couple of the questions a little better.
Screw scientists asking the question. Just
Yeah.
say, That's not enough. That's how low exactly or how high, and does it matter?" Which I think you said very clearly about if it's enough. Does low even matter? Um, well, moving into the new frontier, with this is an exciting moment. You talked about some clinical research. You do some preclinical, some clinical you've been doing recently. The recognition right now with the award. Obviously, there's so much more to come. But what are you excited about, or what's happening in the lab? If you can give us like a sort of peek under the hood of what's ahead, or some collaborations you're doing.
I'll give you something and then I'm going to leave you hanging a little bit
Okay.
for a result. Okay. So,
Okay.
one of the nice things about these methods being a little bit more cost effective, we're really pushing them towards humans, right? So we do these preclinical studies, and I know people struggle with the concept of preclinical studies, and it's a fair thing to struggle with. But we're always trying to see if we can model it in blood and then model in humans, and what does the human blood tell us about the other tissues. So we're going forward with that, and I think we'll have a handful of these clinical studies because sometimes people ran clinical studies already, and the samples are in a freezer and with certain details that we can go back and analyze them retroactively or retrospectively, sorry, and get the some neat results. But one of the things we found that is coming around the corner, and some of this is out there in the public domain, so I'll let that part out, but I won't let the answer out. Is when you consume this DHA molecule, people thought it got back converted, retro converted to another molecule called the EPA. And one of the guys in our lab, Adam Metherall, was looking at these studies with this fancy machine. And that we were talking about where did you come from? Well, he did that with the EPA that was going up after we gave DHA. And he said, where did you come from? And he showed me the data, and it wasn't coming from DHA. if it was this back conversion, it was supposed to look like that, right? And so he did some studies following that up. We got studies we did in humans. We followed it up, and we said, hey, it's not DHA being converted backwards that leads to the rise in this molecule. It's DHA stopping this molecule from being metabolized, so it's going up. It's like DHA saying, hey, there's enough of me. You don't need to make me, because usually we think of this EPA being converted to DHA. So we did a lot of work, and we've shown we've established a step. We've published this, I think, this year or late last year, that there's a step where DHA blocks its own synthesis. We got funding, and we've completed a randomized controlled trial of vegans who are very important to do this, and we got DHA for them raised in algae with a very special weight, and we're trying to establish the dose at which they say, hey, there's enough of me, stop making me. And that way, I think we're going to get a handle on how much you need, right? At least metabolically speaking,
Right.
right? Because it's a feedback inhibition. And when there's enough of you, you can let's stop making me because there's enough. And so we're working on that. We've got the results kind of drafted, and we're starting to present them at conferences, and hopefully this year, but soon after that, we'll have that answer, along with a few more steps on what happens to the conversion rates when you're eating enough or you're not eating enough, right? Because this low conversion rate might not be constant. That's a hint. It might go up and it might go down depending on your needs, right? And so that's something we're hoping to get an answer to, or at least a good hint on how it works.
Wow. Well, hint captured and really, really fascinating. And it sort of just keeps speaking to the body's economy. Like when it's in a healthy state, it's sort of, why would I ask for more or convert more if I have enough? I mean, wouldn't that be nice if our homes and lives work that way, just inherently, and our body seems to? Well, I look forward to more conversations, Dr. Bazinet, with you, but thank you for today sharing all of this new science and sort of putting in a clearer light. I think that that's what you do so well, and it's so exciting to know that science can be so complex, but there are some simple things, simple takeaways like plant-based omega-3s may not just be secondary players. They're essential to this story, is what I keep hearing, to our brain, our body. We spoke about the brain today. It may be part of the main story. This conversation is a much bigger part of a larger novel or conversation to come. And I'm really grateful for you taking the time today, Dr. Bazinet. Congratulations again.
Well, thank you very much, and hopefully in the new year we can do this again. Research takes a bit of time, but we're I'm driving my student nuts getting those results together, kind of writing her a few times a week, asking her for
Oh,
updates, sometimes the same day. So we're working on it.
all right. Well, that's the rite of passage of a grad student for sure. I can attest to that. So well done, Dr. Bazinet. And I'll
Thank
look
you.
forward to speaking to you again. Okay. Be well.
Likewise.